afternoon, everyone, and thanks for giving me the opportunity to be here. I've been listening all afternoon, and some really good content, so I'm hoping I can add just a little bit. And I recognize we're just a little behind schedule, so I'll hit on the high points, and then we can go over questions in the breakouts as needed. If you guys can go to the next slide. Apologies that I'm not able to drive myself the slides today. So I'm representing MISO, the grid operator in the center of the country, Midcontinent Independent System Operator. We run the grid and keep the lights on for 15 states throughout the center of the country and the Canadian province of Manitoba. And I've just got a couple of highlights here. It is a very large grid, and we are part of the Eastern Interconnect as well. So we are a subset of a much larger grid. So when Debbie was talking earlier about the benefits of diversity, geographic diversity, we definitely have that and experience that both within MISO and across the Eastern Interconnect, and I'll talk more about that. So we are about 130,000 megawatt system peak, and of that, at this point, since the focus today is on renewables, of that, about 20,000 peak comes from, 21,000 now comes from wind, and we have almost 26,000 megawatts of wind installed throughout our service territory. Let's go to the next slide. So just to tell a little bit of the story, and I'll continue the story. What I'm going to focus on today is I'm going to talk about forecasting and how we do forecasting, and focusing on wind forecasting and how that fits into our processes. I'm also going to talk about some of the things that we've done, some of the market products we've added, and some of the modeling that we've done to enable specifically wind and now solar to integrate into our grid. But first, I'm going to talk a little bit about how we see things changing, because we think a lot more change is going to be needed in the future. So this chart shows basically my tenure with MISO. I joined in very early 2007 when we had 2,500 megawatts of wind on our system. And you can see today it's kind of been marching up with just a couple hiccups throughout the years, but marching up, and we're now at 25.7. And we expect that to continue through the near future. Next slide. So the Midwest is the, I've heard it referred to as the Saudi Arabia of wind. So we have had quite a bit of wind penetration. Solar is coming now. So you can see that the grid currently doesn't have a lot of solar, but that is starting to really change. And you can see that change coming into play this year as we are integrating close to 2,500 megawatts of new solar in 2021 alone. And if we looked forward into the future, you know, it's always, the next couple of years are difficult because we have an interconnection queue process where all of our participants line up, they queue up to register new resources. We have 100,000 megawatts in that queue, and 60,000 of those megawatts are solar. Another 20,000 are wind. Now, not all of that is going to come to fruition, and that's where the difficulty is. Some of those are speculative, some of those won't win interconnection service, some of those, the interconnection service will be too expensive, but it gives you a sense of what we're looking at. We're looking at a lot of solar coming in the near future. Next slide. A picture of how this wind and solar looks today throughout our footprint, and you can see that, and again, geographic diversity. While it may seem like there's less geographic diversity, every bit helps. So if you can imagine the geographic diversity differences between a California grid where you have a much narrower east-west band than you do a north-south band, versus this band of energy throughout the mid-continent of the United States. So we do have quite a bit of diversity. One of the concerns in a large heavy wind fleet is as the change in wind travels across the territory that you're thinking about, the territory that has the wind, and as that change in wind travels across, if you have that wind typically travels west to east. So if you have a narrower west to east band, it's going to take less time for those changes in wind to travel across that band. So what we're looking at here is, you know, a 8-state-wide region where changes are traveling across the band. Again, diversity really helps. If we were to add on the 100,000 megawatts of solar and wind in our queue, it would really represent an even broader distribution, because solar in our queue is very well spread around our entire footprint. The wind is in the north and central regions of our footprint, but remember, we have a south region, and quite a bit of that solar is going to be located in the south, and it's going to be spread all around our footprint. Next slide. One of the earlier speakers, Aidan, I believe, talked about probabilistic or stochastic versus deterministic. And I'm going to have a slide that talks about one of the products that we've introduced, and I'm going to go into a little more detail here, but I just wanted to mention it right now. One of the studies that we've been working on is called the Renewable Integration Impact Assessment, and it's kind of written there at the bottom. And if you Google that, you can look up RIA, R-I-I-A, Renewable Integration Impact Assessment. And what we've done is studied what renewable portfolio looks like as it crosses through 10%, 20%, 30%, all the way up toward 100% of penetration levels. And what are the impacts to reliability? So MISO's role as the system operator, we're a member services organization. Our job is our members have entrusted us to provide reliability services for their customers. And so what we're focused on is what those reliability needs are going to be 10 years from now, 15 years from now, 20 years from now, as the renewable portfolio, as renewable penetration expands. And one of the takeaways that we have is that variability obviously is going to get much, much greater. So if you just kind of look at these charts, and you see the error bars, you know, the solid bars of where there's a strong expectation, even those are kind of spreading apart a little bit, but then the outliers are getting farther and farther away from the center. And this is MISO's specific system here. So when you're at a 40% penetration level, you have error bars that are 20,000 megawatts on either side. So you have specific one-off scenarios where you can expect to see a 20,000 megawatt uncertainty or variability occurrence on your system. That's not something we can take lightly. Next slide. So before I kind of come back to the present and talk about how the market products that we currently have and the forecasting that we currently do, I wanted to talk a little bit about what we call the reliability imperative. And the prior slide is just kind of one snapshot of a number of different things that have led us to describing the future state of the grid as a reliability imperative. We need to be talking about it, we're doing what we're doing now, and working to prepare the grid for the future that is going to be upon us soon enough. And we think about that in terms of 3 parts. The first one is market redefinition. And I think as I listened to the speakers today, I heard a lot of examples of market redefinition. And market redefinition can be on the retail side. It can be time of use pricing. And I heard examples on the market operator side, the wholesale side, where we operate, of new products, whether they be frequency response products, other kinds of the image where energy typically today is 80% of what the market is focused on, and those ancillary services represent just that last 20%. And then moving to the future where energy is a much smaller piece of the pie, and ancillary services pick up and are much more important and much more necessary. This is what we're talking about when we talk about market redefinition. We have already put in place some of the products and services that have helped us get to where we are, you know, the low-hanging fruit. Some of the decisions and some of the things we're wrestling with going forward are going to need to be bigger. Incrementalism probably isn't going to work this time. So one of the first things that we have already been working on is what we call the market system enhancement. This is the second leg of our stool. And that is an effort to redesign both our hardware and our software systems to be able to prepare, to be able to integrate those markets that we're going to need. We have been operating the same market software, not the hardware, but the same market software for most of my tenure at MISO. We launched the energy and ancillary service markets that we're using today. We did that in 2009. And at the point in time we launched them, that they had already been in use by another system operator. So those softwares date back to maybe the mid to late 90s. Soon after Order 888 is when they were invented. So those designs are, a little out of date if you're using software from the 90s, specifically from a security perspective, from a scalability perspective. The algorithms may not necessarily be out of date, but certainly all of the accompanying software that enables the markets to run could stand for an update. So we have been focusing on, for the last 3 or 4 years, and are continuing to focus through until we get through this, a complete redesign. So we'll have a system that we can much more easily bolt on new additions as they come. And then lastly, and certainly not least, is long-range transmission planning. And I heard Debbie, one of Debbie's conclusions was that transmission is our friend. The center of the country is in a great place because we are an interconnected grid. We have strong ties across neighboring seams. Those ties are already being challenged, and those transfers are already being challenged by the level of penetration of renewables that we have. We're starting to see more and more difficulty for resources to interconnect because there's just not transmission to carry the energy where it wants to go. So long-range transmission planning is the third leg of that stool. A coordinated effort to deliver the transmission system that we're going to need to manage this grid that we're talking about in the future. Moving on to the next slide. And recognizing that I should probably take just about 4 more minutes. So let me touch the high points of this.
Marc, it's okay for you to go over. It's okay. We'll just, we'll just extend it to what you need because it's fine.
Okay, Debbie. So this is the slide that talks about one of the products that we've implemented already. So ancillary services have been discussed. We talked today about regulating reserve, which is that moment-to-moment reserve that's needed. We talked about spinning reserve, I think. This is another ramp product that we've had for 5 or more years now, maybe as long as 7 years. And this is the one where we tried to foresee the need before the need was upon us. Because a lot of times it's hard to foresee those needs, and grid operators often find themselves playing catch up. We're trying not to do that anymore. And this was one of our first examples. This is also the example where we talk about determinism versus probabilistic. And I know a lot of people aren't mathy and sciencey people. And so hopefully a picture might help. This is a picture of our 5-minute dispatch process. So you have these 5-minute timescales down at the bottom. And we're focused on 2 times in particular, 8:10 and 8:20. And our algorithm is extremely deterministic. All of the different forecasts, all of the different variability, all of the different uncertainty are all incorporated into a math problem that assumes no uncertainty and no variability. This is the way it's going to be 10 minutes from now. And it solves the problem based on all of the guesses, assumptions, forecasts that we put in, but then it assumes that they're all exactly what's going to happen. That's what deterministic means, and that's what the markets use. So right now at 8:10 in this example, we're calculating a set of solutions for 8:20, and then we will send those dispatches to our generators. We'll send them at 8:15. Everything takes time. So it is a 5-minute process, but we're always looking ahead 10 minutes to do it. What the ramp capability product does is create these cones. So it's an effort to try to create a probabilistic view within a deterministic process. So we have a specific requirement to reserve back an excess, an available amount of ramping capability so that we can hit any spot within that cone. And then that's for obvious reasons. I've seen lots of charts today that show the variability that's happening because of wind and solar. And this flexibility that we are building in, we build it in every 5 minutes, and it's always made available for a 10-minute stretch. And we can deploy it when we need to, when the wind capability or the load capability is falling far outside that deterministic view. So it's a market-based approach. It's a systematic approach to pre-position resources. And really, it's a way to intentionally incur a little bit of cost in an effort to save more money over the long run by reducing price spikes and volatility in our market. Moving on to the next slide, thank you. Let me tell you a little bit about our dispatchable intermittent resources, which I think is kind of old news now. We introduced it in 2011. At the time, it was a novel concept in system operations, but has, I think, widely been used, at least through parts of the United States, where 5-minute dispatches are utilized to integrate wind and solar into the footprint. And you talk about a set of market software, market algorithms that were designed for a different time. Our market algorithms basically ignored the wind resources that we had in place. And that was fine when we had less than 500 megawatts of wind resources on a 120,000 megawatt peak system. But once we started seeing considerable wind penetration, and the wind was trying to produce energy and causing congestion. All energy producers cause congestion. We're not singling out wind here. But as congestion happened and our market was not aware of it, we were seeing bad market outcomes, and our operators were needing to work around it. Whenever we don't have a market solution, in any of these system operations conditions, whenever you don't have a market solution, your operators are tasked with doing that. And if we think to the future, if we think to DERs, if we think to widespread distributed resources, it's not going to be fair to our operators to be forced to be requiring them to be making manual operations. So we had a taste of this in 2008, 2009, when our operators were making hundreds of phone calls a day. And that's why we introduced DIRs, which is a pretty simple solution. It basically found the question that we answered was, how could you make wind look like all of the other resources in the software? What would you need to do in the software to make wind able to participate? And we found that we only need to make a couple of small changes to make that happen. So we have slowly been moving toward getting all of our wind and solar registered as DIRs, dispatchable intermittent resources, and moving forward, all of our solar and wind as they interconnect will be dispatchable. Next slide. So I've spoken about a little bit of this. A couple of the most important parts. I said that we tried to do as little as we could to make these resources look just like all of the other resources. And the primary difference is with a wind resource and now a solar resource. I speak of wind more than solar, which is different than the rest of the presenters today, because we have a lot more wind than solar. But that's going to be changing maybe in the next 5 years, maybe as soon as that. The thing that's different is you're not sure what it's going to be capable of. And the longer you wait, the better you're going to have an idea of what it's going to be capable of. So we allowed their 5-minute forecast, which they can provide almost right up till the last moment when we're about to run our software. That becomes the limit that we use within our market algorithm. We have our participants can create their own forecast and provide it. However, MISO also creates a forecast for each of our resources. We prioritize that from the very beginning. And more than 90% of our participants use the MISO forecast in order to dispatch their resources. What that means is our forecast needs to be good. We have a determinant, like I said, we have a deterministic software, which means that the maximum limit of each of these wind resources becomes a limit that we will dispatch to, because wind is so cheap. Unless it's being constrained because of congestion, we're going to try to have all these resources at the top, so that what the top is becomes very important, and how well we're forecasting what the top is every 5 minutes throughout the day is very important. Next slide. So let me back up just a minute before I go into detail on forecast. This is where we use our forecasts. We have a medium-term load and renewable forecast and a short-term load and renewable forecast that we use. And our forward process we have a forward process that does commit resources for long lead times greater than 16 hours. And that's when we're making decisions. That one often does not come into play, but in situations like the winter event that we just went through, that becomes a very important process, especially since the Monday of that winter event was a holiday, and gas markets are closed on holidays. And so gas purchases were all happening on Friday. So our participants are trying to determine what the right amount of gas to buy is, and our operators are trying to determine whether or not these different long lead time resources will need to be online. And of course, how much wind we have available is going to very much come into play in that question. So that's what we use that forward commitment process for. And then on an ongoing basis throughout the day, we have an intraday commitment process that's looking ahead, focusing on 4 hours from now, all the time 4 hours from now, but that 4 to 16 hour window, looking at the load forecast, looking at the renewable forecast, and making commitments, additional resource commitments as needed based on those forecasts. And that goes all the way down to the 5-minute market that I talked about, where our short-term renewable and load forecasts ultimately become entry points to the deterministic algorithm, where whatever the forecast is with 5 minutes to go becomes the product. In terms of the load, that's how much load we are targeting to buy. And in terms of the renewable forecasts, each of those wind farms, that's going to be how much they have available to offer. Next slide. And I will wrap up here. Let's actually skip this slide since I talked about this a little bit already, and skip this slide too. Okay, so what goes into our renewable forecasts? Quite a bit of information. I think somebody talked about cameras, and we don't have cameras yet, not quite as important for wind farms, but I found that interesting. So maybe that'll be a data point in the future where we have cameras on solar collectors. But we have some of the non-changing information, operational characteristics, which I'll come back to, longitude, latitude, which helps form the weather prediction, and then the basic information about each wind farm. And then what's going into that on a periodic and frequent updating basis is the numerical weather prediction, which is basically taking the live atmospheric data and creating a prediction about what the wind patterns are going to be for the next 5 minutes, the next hour, the next 16 hours. And then that live data as well from wind sites, wind speed from wind sites is going into a set of models that we have and producing a forecast. Next slide. We have forecasts that are happening and they're updating every hour, and they are building off of past success and past failures. So you can see here an example of how the actual wind is the black line, and we have a series of wind forecasts that are being made prior to 1 hour, 2 hours, 3 hours, and 4 hours prior. And they are updating and trying to correct for what is actually happening. So what we see, the blue line is the oldest one, and the blue line is predicting that the energy is going to drop off, but it missed the peak. And so as the peak is crossing through, as the actual energy is crossing through and preparing to cross through, the forecast is updating and trying to capture what it thinks the new peak is going to be. Next slide. Switching gears a little bit, that was a forecast tool on our broader forecast. And we also have, like I said, a forecast for each of the wind farms in our footprint. And market participants do not have to use our forecast. We use our forecast for certain processes. Our market participants don't have to use our forecast, but 90% of them do. And we have monitoring and reporting on how each of those forecasts are doing. So here you're looking at a single wind farm, and you're looking at forecast error, and as it grows there for a certain time period, that's going to kick off a monitoring alarm for our forecast operators to adjust and to look into. Next slide. And let me finish it up here, and then trying to catch us up just a little bit. I talked about the specific operational conditions, and this has become important in the news lately. For MISO, this was an issue a few years ago where we had a severe winter event, a very, very cold winter in the northern portion of MISO, and did have some significant wind cutouts. And after that time, that put an emphasis on our part on making sure we have an understanding of all of the wind farms and the characteristics of all of the wind farms in our footprint. And that includes when you could expect turbinizing, when you could expect a high-speed cutout. Are there high or low temperature turbine cutouts? Those are some of the things that are specific to each wind farm, and we are now tracking, and that goes into both our long and short-term forecasts. A couple of other things that we think about, and this is just kind of to leave you with something to think about for the long term. A couple years back, we had a 72-hour period where there was zero wind production. The wind basically stopped. So low to negative production periods. The sun did go down 3 times during that 72-hour period. So we are going to have to think about other ways to manage some of these extreme scenarios. You think about a 100-year drought or a 100-year flood. Well, we will also have to be thinking about a 100-year low wind event and a 100-year cloudy event. Having grown up in Michigan, that felt like every day to me. But those are some of the things that we're going to have to think about moving forward. That concludes my presentation, and again, appreciate being here and looking forward to the chat.